Okay, so let's start this seminar from Tom Howe. Tom Howe is from Caltech. He's a very old friend of the laboratoire. He has he knows many people there. He has visited a lot. And today we'll speak of potential singularity for the 3D incompressible Euler equations. And we'll show a beautiful picture showing how ZL will develop. So Tom, you can go.
Okay, thank you. I would like to take this opportunity to thank Francois Murat and the rest of the organizing committee for inviting me to give this Zoom seminar in the laboratory of Jacques-Louis. Today I will want to speak some recent work on this potential singularity of 3D incompressible Euler equation and the nearly singular solution behavior for the 3D Navier-Stokes equation. And I will also review some previous work with my former postdoctoral law and my former PhD student Pengfei Liu and my current student Jiajie Chen and De Huang. Okay, so this is the 3D incompressible Navier-Stokes equation. So U is the velocity field, P is the pressure. So this is the diffusion term. So nu is the constant diffusion term. Incompressibility means that the U is divergent free. Okay, so the 3D Euler on Navier-Stokes equation is so challenging because you define the vorticity as the curve of the velocity field, and then the vorticity satisfy this equation. So vorticity being transported by the same velocity field, but also produce a vortex stretching term, which is a scale like a quadratic nonlinearity, because you can recover velocity field from the vorticity through the so-called Biot-Savart law. And gradient U is a Riesz transform, is a Riesz operator of degree 0. So you can bound gradient U from above and below by vorticity in LP norm for any piece greater than 1 and less than infinity. So formally, this scale like omega squared nonlinearity, but because it's a non-local operator, so they don't exactly align to make this nonlinearity scale like omega squared. If this is really like omega squared, we know that it will blow up for large initial data. But so far, the incompressible Navier-Stokes equation is only known to exist for small data. Small data, you have global regularity. So this is the result. So small in the sense that the initial data either in LP norm p greater than or equal to 3, or in this dimensional invariant product of the initial data being small, and then you have global regularity. So there are other various kind of non-blow-up criteria due to different people, like this is due to Prodi and Serving. So basically control the LP norm of the velocity field, but it's LQ integrable in time with P and Q satisfy this inequality. So basically this condition is to make sure that under this condition, under the a priori energy estimate, that the viscous term somehow still dominate the nonlinear term in the convection and the water stretching. And there was the special case when p equal to 3, meaning that if you have a control of the velocity in L3 norm, but uniformly in time, then there's no blow up. So that is only available much later in time. And there was a very well-known so-called partial regularity result due to Caffarelli-Kohn-Nirenberg in 1982. So basically say that any suitable weak solution of the 3D Navier-Stokes equation, if there's any blow up, the set of singularity in space-time, the one-dimensional Hausdorff dimension of this associated singularity set must be 0. So for the axisymmetric 3D Navier-Stokes equation, that's what I'm going to focus on today, that there was additional non-blow-up result by these two groups in 2007. So basically, you say that the if U blow up like a 1 over capital T minus T to the 1/2 power, it's not strong enough. So that's it's a critical case. So Larray proved that if C is small, and then it does no blow up. So they show that any constant C. So if U blow up like almost like a self-similar scaling, and plus this additional condition, then there's no blow up. So for Euler equation, there was a number of criteria for non-blow-up. The well-known one is due to Buchanan-Maida in 1984. So basically, you say the vorticity had to blow up. Moreover, the maximum normal vorticity in space. It's not integrable in time. So my early work was inspired by the work of Konstantin Pfefferman-Maida in 1996, where they realized that the vorticity vector regularity can also help to deplete the potential singularity. So the vorticity vector regularity, meaning that if the gradient of the vorticity vector, it is integrable, the maximum norm is L2 integral in time in a small neighborhood that contain a maximum vorticity, plus assuming the velocity field does not blow up in time, then you can exclude blow up. So inspired by this result, with my former postdoc Jen Deng and my former PhD student Xingwei Yu in 2005, so we established a Lagrangian version of this result, meaning that you follow a small vortex line segment, and the length of the segment allowed to collapse to 0. Here, this regularity result required the domain to be order 1, cannot swing to a point. So assuming that the vorticity vector are well behaved in the order 1 region seems to be too strong. So we would like to see if you have a potential cell similar kind of blow up, so that would be a 1-point blow up. So we can relax this condition to up to a vortex line segment, but the vortex line segment, the arc length can collapse to a point as long as the curvature, this other curvature in 3-dimensional filament, that are integrable in space, in this local vortex line segment, plus that we, instead of assuming velocity field being bounded, we only assume that the maximum normal velocity field in this local segment are integral in time, right? So that is what we obtained back then, 2005. And 2 years ago, there's an exciting result due to Tariq Al-Gindi. He proved that 3D Euler equation develop a singularity for as a symmetric flow without swirl, but working for very weak initial condition class for vorticity in C alpha class. And alpha are arbitrarily small, make very, very small. So we know that for 3D as a symmetric Euler equation without swirl, if you have a smooth initial data, that it cannot blow infinite time, you have global regularity. There's no water stretching in that case. But when you work on a very weak class, then you could have a singularity. That's quite surprising. At the same time, there's been a lot of effort. People try to look for a numerical singularity, because theoretically it's very hard to prove. Either you cannot prove there's no blow up, but it's very hard to construct a analytic blow up example either. So a lot of this is a long history. This is a partial list, a long history of research devoted to looking for numerical singularity. Okay, so starting from Brown and Stereo in 1991, this was as a symmetric 3D Euler equation. They found there's a potential blow up, but away from the symmetry axis. And later on, Weinan and Qiwang Xu, they were trying to reproduce a result by using the Kuznets equation, and they see no blow up. So I did some work with Professor Rowley in 2006, inspired by the early result by Bob Kerr, where he computed this as 2 antiparallel vortex tube. So this is a paper we published 2006 with Rowley. So this is a triple periodic boundary condition, periodic in 3 directions, as in the periodic box. You have a 2 antiparallel vortex tube rotating in the opposite direction. So it's well known for Navier-Stokes equation, you have vortex reconnection, right? But when you have no viscosity, one may think that there was if the flow still goes through vortex reconnection, meaning that the 2 tubes trying to contact each other, that would be a finite time singularity. So at t equal to 6, they have a very they trying to contact each other, but become flattening. The local geometry become important. So this is the upper half of the vortex tube, the isosurface, and maximum vorticity enter in this roll up region. This is the vortex line. What is vorticity direction going this way? You can see the vortex line is very regular. So that can somehow almost satisfy the non-block criteria that I developed in my postdoc and my former student Xingwei Yu. So we suspect that maybe there's no blow up in finite time, although Bob Kerr presented result that seem to suggest there is a finite time blow up. Indeed, when you look at the vorticity equation, you look at the absolute value of vorticity. So this is the vortex stretch in turn, you project it to the unit vorticity vector. So this is how much it can grow, supply the growth of the amplitude of vorticity. So if there's a finite time blow up, like 1 over capital T minus T, that's what Bocker predict, then that it should grow like this. This right-hand side should grow quadratically as a function of omega square. But we have the numerical data. We're using a spectral method with about 2,000 square cube resolution. You can see this is how much it grows, much slower than omega square, than the quadratic nonlinearity. That formal analysis would suggest this scale like omega square, but there's a lot of cancellation going on due to this non-locality of the kernel. So actually the actual growth bounded by omega times log omega. It's very weak nonlinearity. Then you can actually show that if this is the case, you divide by omega over here, you can get the dynamic growth of log omega with bounded by C1 log omega. That means omega itself can only grow double exponential in time. In fact, if you take a double log of maximum multiplicity, it doesn't grow faster than linear. So there's a lot of potential cancellation going on in the 3D Euler equation. So that's why it has been a lot of false alarm. A lot of people trying to predict a singularity through numerical computation, but later on has been disproved using a more careful numerical computation. So to get some understanding why there was such a cancellation, why it's so hard to get blow up in 3D Euler on our still equation. So with Coming Lee is an excellent analyst. In 2008, we published a paper in CPAM. So by studying the axisymmetric 3D Navier-Stokes equation through this change variable, so this is the angular velocity field, angular vorticity, and angular stream function. And this three function has to be an odd function of R. R is the polar, the cylindrical coordinate, the radial direction, the cylindrical coordinate, right? So then you can derive an equivalent equation for U1 omega 1 psi 1. That's a removable singularity at R equals 0. So you get this equivalent equation for vorticity for this new variable. So we know that for from the Cavalli-Cohn-Nuremberg partial regularity result, that the space-time dimension of the potential singularity set had to strictly less than 1. So that means that for as a symmetric Navier-Stokes equation, 3D Navier-Stokes equation, the singularity has to occur at R equals 0, the symmetry line. It cannot occur away from the symmetry axis because that would be the singularity set in space alone would be a circle, would be one-dimensional already, right? So we would like to derive a one-dimensional model at R equals 0 because that's the only place Navier-Stokes can blow up by dropping the R derivative, right? Assuming that the blow up is flat, like here, locally flat. The Z direction is more singular than the radial direction. So then we derive a one-dimensional model. You can derive a closed model for this axisymmetric 3D Navier-Stokes equation by dropping the R derivative, right? Turns out that this equation is closed. So in more surprisingly, because we define U1 to be U theta divided by R, omega 1 is U omega theta divided by R. So if we assume U1 omega 1 per psi 1 are the exact solution of this 1D model, to our surprise that when you multiply R, you can reconstruct the three-dimensional angular velocity, angular vorticity, angular stream function. They are the exact solution of the 3D Navier-Stokes equation. So in some sense, although we drop the R derivative to derive this one-dimensional model, which is exact for this special class of initial data, has this separation variable. Because, if the initial data is R multiplied a function of Z, the same thing for omega theta, R multiplied a function of Z, then this will be exact. So in some sense, the 1D model capture the essential linearity of the 3D Navier-Stokes equation at R to 0. So, but to our surprise, that for some time that we thought that this would be much easier to work on the one-dimensional model than three-dimensional problem. But if you use the same kind of energy estimate, you encounter the same difficulty. The one-dimensional model is not easier to prove this blow up or no blow up than the three-dimensional problem. But one day I discovered a very surprising cancellation effect. In some sense, you can construct a Lyapunov function given by this U sub Z and V sub Z. So U tilde is a U1, and then V tilde is the integral of omega 1 in Z. So it turns out if you differentiate the equation in both sides with respect to Z, so then the differentiation, the convection term and the vortex stretching term cancel each other. There's a one term that exactly cancel, right? So you can arrive at this almost get the Lyapunov functional. You want to construct the u sub z square plus v sub z square. So that is a positive Lyapunov functional. But still couple the cubic nonlinearity. But there's a minor miracle here. There's a minus sign here. When you add them together, they exactly cancel. So you get a new conservation law for this u sub z square plus v sub z square. So then you get the maximum principle with or without viscosity. So in this case, it's very surprising that you can see that the effect of the transport, the advection term, and the nonlinear water abstraction term for this one-dimensional model have the exact cancellation. And based on this new maximum principle that we have obtained, we can prove global regularity as long as the initial condition is in C1 or any class greater than Cm, greater than C1, right? So you have no blow. And based on that, you can go back to construct a family of a large initial data for 3D Navier-Stokes equation. You need to add a correction here so that you have finite energy. So that we can construct a family of a globally smooth initial solution for 3D Navier-Stokes equation, but they are not small data. Okay, with finite energy. So for a long time, I tend to believe that maybe there's no blow-up in 3D Euler Navier-Stokes because there's some very subtle cancellation going on. Until when I worked with my former postdoc, Law, in 2014, we published a paper that generated a lot of attention. So in this paper, we consider a geometry as a symmetric geometry. So periodic in z direction, there's a solid boundary R1. So the solution is an odd function is function of z. It's an angular vorticity, angular stream function, angular velocity field. Our odd function is function of z as a symmetric with respect to r. So the top flow will be swirling downward counterclockwise, and the bottom is swirling up clockwise. So create a compression along the z direction. So the singularity occurs right at the boundary at the symmetry plane, where we play the odd symmetry is equal to 0. So you can see the vorticity enter from the boundary enter into the interior, and then suddenly change up or down. So the vorticity direction is not smooth. And also this is the stagnation point when the velocity field equals 0, right? And this whole ring becomes singular. This is for the 3D Euler equation, no viscosity. Okay, so then there's the stabilizing effect, the advection term that I just mentioned earlier, get penalized at this corner, at the singularity position. So this is the flow, it's a hyperbolic flow at r equal to 1 as z equals 0. And there's a bottom one that exactly go the opposite, right? The flow going like this to go like this. So we use the same as the formulation that I introduced with Kunming Lee in the same CPAN paper. So we work on the U1 omega 1 per psi 1. By initial data, now the 3D Euler equation, no viscosity. If a very smooth initial data is driven by large swirl, so it meaning that only non-zero component is the angular velocity field, but the other two velocity fields are set to 0 initially. So this is in a short time, it's 0.03505. You can see that the absolute value vorticity develop like a delta function, like singularity at arc 1 and 0, 0 along the boundary. It's not along the symmetry axis. So we try to solve this equation by making a change variable to the rho and eta plane by zooming the singularity, by constructing a moving mesh map analytically. And from time to time, you will update the map. So then although the solution develop a physical singularity in a finite time, looks like infinite time, but when you work on the transform domain in rho and eta, you always work with a smooth function, right? So you can use a 6th order method in space and 4th order in time, adaptive mesh in time, you get a very high accuracy. So when you, for example, when you increase the resolution in rho and eta to up from 1000 to 2000 square, the corresponding mesh in the physical domain, R and Z, is like a 10 to the power 12. You have an extremely dense mesh resolving this singularity region, right? That's why this is the profile that in the transform domain, rho and eta. And then we check some quantity to conserve quantity. The energy is supposed to conserve for 3D Euler. So indeed, it conserves to 12-digit accuracy, so you increase the resolution. And the total circulation is conserved. There's two total circulation quantity. One is 0, one's the maximum total circulation. And they also conserve up to very high number of digits. And you can try to fit the asymptotic growth rate, right, as a function of time, to see if it's said that the Buchanan-Maida block criteria, the maximum vorticity should not be integral in time. So then we get a very convincing fitting that this exponent is about 2.4579. So certainly greater than 1, it's not integrable in time. You use a 2 different ways to do the fitting to get the exponent and the scaling constant, and they all converge up to 3 or 4 digits accuracy as you increase the solution, right? And we can also push, because the highly adaptive mesh, we can push the singularity computations very sufficiently close to the predicted singularity time, up to 7 digits of accuracy, which is never has been achieved before in the literature. So in the same paper, we proposed a one-dimensional model because it looks like the symmetry, the asymmetry along the z direction and the presence of the boundary at arc 1 played a very essential role to produce this stable blow-up scenario. So if you make a change variable, you call u1 squared to be a theta, like the density in the 2D Bushnell equation. You call the axis velocity field to be u. So you can derive an exact one-dimensional model at arc 1, because there's no flow boundary condition. You can drop the radial derivative at arc 1. You need to reproduce a approximated Biot-Savart law to close a one-dimensional model. So if you further assume that the vorticity does not change if you go from boundary arc 1 all the way to minus r and minus infinity, then the Biot-Savart law will reduce exactly to u sub z with the Hilbert transform of vorticity. In fact, that this simplified Biot-Savart law has been used in different models in the previous literature. So this is a closed model. It shares all the symmetry scaling property of the original 3D Navier-Stokes equation. In fact, you can show that the 1D model produced the vorticity qualitatively same as the 3D vorticity, the omega 1 arc 1, and the velocity field also have the same scaling. Okay, so in the subsequent work, so we together with Sasha Kiselev and Radimir Zverik, so we actually been able to prove this rigorously. We published in CPAM 2017 a paper that this set of author that this one-dimensional model actually develop a finite time singularity, and the asymmetry and the scaling property, some monotonicity of the reduced Biot-Savart kernel played a very essential role in this analysis. So this work has been published in about 7 years ago, and since then it generated a lot of interest in the mathematical community, so especially in the PDE community. So for example, Kiselev and Zverik resolved a long time open question in 2014 that we know 2D Euler equation cannot develop a finite time singularity, but the analysis showed that the gradient of vorticity is the maximum principle, but gradient vorticity can grow double exponential in time. So for a long time, people was not sure whether or not this is an analytic overestimate or it can be really realized, right? So using the same setting with the presence of the boundary on the circle and the asymmetry, they can actually prove that this double exponential growth can be realized. So this published in the Annals of Mathematics in 2014. And also in 2016, this set of authors also proved a family of a model ranging from a 2D vortex patch model to all the way to the surface quasi-zero-traffic SQG model. But for vortex patch, under assumed vorticity is piecewise constant, but it covered the boundary, the support of vorticity kind of intersected the boundary. So but the presence of the boundary again play a very essential role, so they can prove rigorously that for this whole set of family of vortex patch problem, if you develop a finite time singularity. So with my former PhD student, Pengfei Liu, we're trying to develop a program to see if we can actually rigorously prove what we observe with Guo law can be justified rigorously, because computationally we find it very easy to reproduce, very robust, the blow up, and it seems to be very convincing. So we make an analogy with the 3D symmetric Euler and the 2D Bushnell equation, right? Because the singularity occur at arc 1, not at arc 0. So these two equations have the same scaling property. So if you again let U1 squared to be theta, theta is the density for the 2D Busnets equation, and omega 1 is to be equal to omega in the 2D Busnets equation. If you look for cell-similar blow-up for the 3D Euler equation, and then it turns out that this additional term from the 3D Euler equations are asymptotically small, vanishing. So they're really scaling equivalent. So for that purpose, we just focus on the 2D Busnets equation as the first step. We adopted this so-called dynamic scaling formulation that I learned first from Professor George Papanikolaou when I was a postdoc at Curran. So at the time, they're trying to solve the nonlinear Schrodinger equation blow up, especially the critical case. So they're using a so-called dynamic scaling approach, meaning that when you're trying to study a potential focusing cell-similar blow up of a nonlinear PDE, it is not so easy to solve numerically, right? Instead of using adaptive mesh, so they basically trying to zoom in the singularity by stretching the focusing singularity to be order 1 region, to a cell-similar profile, and also we scale the maximum of this broad quantity to be order 1 by some normalization condition. So basically, they introduce a stretching variable CL, trying to, instead of allow them focusing, you're trying to push the support to be order 1 region, and also introduce a damping factor, C omega and C theta, so that you normalize the maximum of this blow-up quantity to be order 1 using some normalization condition. And these 3 parameters have to satisfy a linear relationship to be equivalent to the original PDE. So you have 2 degrees of freedom, so-called normalization condition you need to choose to get an equivalent equation. So this is the equivalent set of equations. You can justify them rigorously under this scaling relationship, right? So if theta, omega are the solution of the original 2D Busnets equation in the physical space, and through this scaling with this capital C theta, CL, C omega defined by this way through the little parameter, and then this you also rescale the time, right? So that will be completely this rescale equation solution will satisfy this rescale dynamic rescale PDE. And the rescale time is also interesting. So you rescale the time after you do the rescaling, the rescale time will go to infinity. So the singularity time will correspond to this rescale time go to infinity. But if you have a damping here, meaning that if the omega, expect omega to blow up, so you have to put a damping here. C omega is be negative, right? So if you can show that C omega converge to a limiting constant which is negative, as the rescale time go to infinity, then when you map back to the physical time, that become a finite time singularity in the physical space, in the original XT space, right? So we use this formulation to investigate the potential singularity, and actually people like Frank Burr and a lot of analysts further develop this technique. So I mentioned here as a so-called modulation technique. It's become a very powerful PDE tool to analyze the finite time singularity of a nonlinear PDE. So we try to adopt this framework to have a computer-assisted proof for finite time singularity of the 3D Euler equation. So the idea can be formally described as follows. So this is the dynamic variable, the vorticity and the density for the 2D Busnets equation. You can formally write it as a dynamical system. So this is a non-local nonlinear equation. Through the Pearson law is also non-local. But we don't know whether or not it can develop a non-trivial steady state. So that will correspond to a cell-similar profile. But since we can, through the dynamic scaling, you have a smooth profile. It's a bounded profile because you also normalize the maximum to be order 1, basically, right? So numerically, you can construct a very accurate approximate steady state we call U-bar with a very small residue that we can control, like a 10 to the -8. That's something we can do. In fact, for the computation that I did with Bohr law, the conversion to the steady state occur very quickly. You can drive this epsilon to 10 to the -8 or 10 to the -10 if you have enough resolution. So then you would like to construct a perturbation, the U tilde, we call U tilde, right? So this U bar is not an exact solution. We have an error as residual error. So you want to construct a perturbation analytically to show that there exists an analytic perturbation so that the sum is the exact solution of the original dynamic scaling equation. So the perturbation for U tilde, you can derive it for this equation. There's a linearized term, there's a quadratic nonlinearity because capital F is this quadratic nonlinear the convection term, water extraction, the only quadratic nonlinearity. So this is the only nonlinearity term you have, and this is the residual error that we introduce. So if you can show that the linearized part of the equation of U tilde, if you ignore the nonlinear part, because the U tilde is of the same order as epsilon. Epsilon you can make very small, so it's a weak nonlinearity theory, right? So the key part is whether or not you have a stability for the linearized equation given by this guy, right? So if the linearized stability in the sense that if this semi-group of this linearized operator have a damping effect, meaning there's a possible, there's a spectral gap, meaning that the real part of the eigenvalue should be negative or negative. In fact, that's what we observe numerically. But you need to prove rigorously there's a spectral gap, right? So that in the sense there's a positive lambda here, right? And then you can use the Duhamel principle to write the perturbation in terms of the linearized operator. And if you further assume that using the same like weighted energy norm, weighted H1 norm, you have nonlinear stability, then you can derive a norm estimate, energy estimate for the perturbation in terms of the quadratic nonlinearity, because this is quadratic nonlinearity, but you have a damping for the linearized operator. So then you can show using energy estimate a bootstrap argument that if the perturbation remains small in an energy ball of size A, the radius about order epsilon, right? You can, if A is order epsilon, you can satisfy this inequality. Then you can never escape this ball. So the perturbation will remain small for all time, for t goes all the way to infinity. So that will be sufficient to establish a finite time singularity for this dynamic scaling formulation. So we find this method is very powerful because without the computation, you don't have a candidate for possible blow-up solution, right? So with a candidate blow-up solution, you can interpolate in the whole space through some basis function. So you have a approximate steady state, a cell-similar profile at your hand. Then the only thing is to analyze the linear stability using some singular weighted sublet space. And together with my student, Judge Chen and De Huang, we have been very successful to obtain several results. Ultimate goal is to prove the smooth initial data with boundary, the same setting as my computation with Guo law, we will develop finite time singularity. We are not there yet, getting close. So first of all, we recently published a paper in CPAM that the 1D Gregory model that developed a finite time singularity. This model has been very difficult to prove the singularity because again, the competition between the erection term and the water extraction term seems to almost cancel each other perfectly. But we showed that on the real line, the whole line, there was a complex support initial data and C infinity initial data that would develop an expanding self-similar block in finite time. So that's kind of surprising. In the circle, people tend to believe for periodic initial data that people tend to believe there's no finite time block. So inspired by the recent result by Terry Elgindi, so we generalized some of his technique. We can prove the 2D Bushnell equation and also 3D as a symmetric Euler equation with boundary, the same setting as in my computation with Guo law, but for C1 alpha initial velocity field, right, for alpha small, with finite energy, develop a finite time singularity. So that is one step towards the proving the smoothness in initial data. The C1 alpha class is important because if you make alpha very small, the effect of the transport, the convection term, the stabilizing effect has been substantially weakened dynamically. So there's a small parameter you can play with. And recently we just submitted a paper, posted in the archive, that the 1D HL model that I mentioned earlier, that for smooth initial data with complex support, so that is a big step from C1 alpha initial data to C infinity initial data with complex support. But we have been successful doing that using the framework I just outlined here. We just submitted to annual of PDE. So with that, I want to switch gear to the more interesting result that I would like to present today. So this is all the result I presented up to here. It is for the potential block at the boundary, R1. As I mentioned many times, that the presence of the boundary played a very essential role. In fact, in the same computation with Guo law, we actually originally tried to do it, get a singularity at R0, but we failed because it seems such a singularity for 3D Euler, if it exists, it's highly unstable dynamically. So you can get very close to it, but then it always find a way to escape. So it is the same setting as I demonstrated earlier. So 3D, we compute both the 3D Euler and Navier-Stokes equation. For 3D Euler equation, when you drop the viscosity term, I present you some convincing evidence that the 3D Euler seems to develop a singularity in finite time. But when you add the viscosity back, I also present will present you some very interesting result. The 3D Navier-Stokes equation almost develop a singularity in finite time, but somehow it managed to escape in the last minute. So it is such a blow up for Navier-Stokes, if it exists, could be highly unstable. So there's an unstable direction that the solution can escape. You can get close to it, but you cannot really reach it in finite time. It's the same setting as I showed earlier. So I will skip this part. So this is very simple initial data. This work was inspired by my recent work with Huang, where we find a two-scale traveling wave singularity at arg 0. But the two-scale singularity does not survive the Navier-Stokes regularization. If you apply the constant viscosity, it will kill the singularity. So after that, I tried to find a different scenario that maybe the Navier-Stokes equation, Navier-Stokes regularity, the diffusion regularity with constant diffusion may still survive. So this is a very simple initial condition for the U1. It is completely driven by SWOR, very smooth initial data, periodic in Z direction. It's all function in Z, very fast decay in the radial direction. And the initial condition for omega-1 is 0. Right? It's the same setting, similar setting like in my computation with Guo. It is a tornado type of singularity. This is 3D Euler. Let me show you some examples of 3D Euler. So nu 0. So that you start with a solution is very not highly focused. It's all the one region. The vortices have a very smooth profile in the whole all the one domain. And then it develop a tornado type singularity, in the sense that if you start the initial, the streamline of a velocity field, then you get sucked into the symmetry axis, swirling and go upward, and then go probably outward and then come back again, right? Like a circle. This is a different initial position of the streamline. You can see tornado kind of singularity. And then you get very close to the center of the singularity. So the singularity actually approach to arg 0. So you can see that you get huge amplification of vorticity. But for at the same time, if you study from a little bit away from arg 0, become highly oscillatory. Right? It's kind of spinning around the symmetry axis. So this is the mechanism. It's a dipole-driven singularity. So this is the velocity field, 2D velocity field, and this is the omega-1 contour, the vorticity contour. There's a two, and due to the asymmetry, you have generate a dipole structure. So you generate a negative radial velocity field that push towards the arg 0. This is the symmetry axis, and then because it's incompressibility, it's like a arg 0 is like a wall, impenetrable wall. So you have a hyperbolic flow structure going up or going down like this. So this is a schematic picture. The maximum U1 occur at this position, right? So it's very important that the flow will get squeezed very close to 0, so that it will not get transported away from 0. So that it will go singularity occur at the origin right here, right? So you have to design the initial data in such a way that you not get carried away from the origin, right? The flow tend to push the potential singularity away from the origin, right? So that's why it's very hard to get a blow up in 3D Euler equation at arg 0, because this is hyperbolic. The flow structure tend to somehow dynamically deplete the singularity. So this is the radial velocity field and the axial velocity field. So you can see they create a very sharp gradient, right? So the flow is the negative velocity field. The blue means a negative velocity field. The radial velocity push this way, right? And then this the axial velocity field. This region means a very large positive, so you push up, right? But there's a negative velocity field here, push towards the symmetry axis, and then push away, right? So this is this referring to this picture, right? So for 3D Euler equation without viscosity, it can develop a very sharp front, which is very hard to resolve numerically. So we cannot go very far with. So this is the U1 quantity, which is part of the vorticity for the 3D as a symmetric Euler. you can see they develop like a delta function type of singularity at origin, right? It's in the physical domain, R and Z. But since we can do all the computation in rho and eta, you can see that we're zooming this singularity, so you get a very smooth profile. We only compute in this regime, right? So that shows the effect of the adaptive mesh. So this is the top view of the U1 and the omega-1 variable. So you can see that the omega-1 is vorticity develop almost like a one-dimensional delta function structure, right? As a curve. This is the adaptive mesh. You can see the densest mesh centered around this most singular region. This is the U1, right? It's a traveling wave solution that this is the maximum U1 kind of traveling towards the origin, right? That's how it works. So we monitor how much the vorticity amplify compared to initial vorticity. You can see that for the 3D Euler equation, you amplify by a factor of 5,000, right? And you want to make sure that you satisfy the Buell-Catton-Meier condition, you integrate the maximum vorticity along time. You can see that also blow up, seem to blow up in finite time. So you can see that the water stretching alignment is the U1 equation given by this right-hand side, right? This is about transport. So psi sub z and the U1, the alignment, strong alignment of this give you quadratic nonlinearity, right? So quadratic nonlinearity means that you will have U1 to block 1 over t, right? So you can see the maximum vorticity and psi sub z, they have a strong alignment here. Right? It's a relatively flat region here. So it pushed up this U1 in this portion. We also do a careful resolution study, make sure that the maximum vorticity is well resolved in different mesh. And this the order of accuracy is better than second order accuracy, right? Second, third, and fourth as you refine the mesh. So we do some scaling fitting for the maximum vorticity inverse to see does it really block like 1 over capital T minus T. You get a very strong fitting. Is the R squared statistic. It's very close to 1, right? 1 would be perfect fitting. So you get a very convincing blow up the capital maximum vorticity blow like 1 over capital T minus T, so certainly satisfy the Buell-Catton-Meier condition. And the maximum velocity field scale like a 1 over square root capital T minus T. So that is very interesting because this is the scaling, the Navier-Stokes equation also is supposed to satisfy. And the U1 omega 1 blow like a 1 over capital T minus T, as I mentioned before, you get a very, very strong fitting. So everything seems to point it that out that we have a one scale locally self-similar blow up with a scaling the R and Z. R and Z are the position where you want to achieve its maximum. It's the traveling wave that at this position approaching the 0. But with this scaling, the Z is the how fast the self-similar scaling swing to 0. In my previous work with De Huang, we find a 2 scaling singularity, meaning that this scale like a square root capital T minus T, the R, but Z is like a linearly vector T. So the ratio is not the same order. So they will not survive the Navier-Stokes regularization. But here, for this new type of initial data, we find that it survived, the scaling seems to survive the Navier-Stokes regularization. So you can see that the self-similar nature of this potential block of 3D Euler. So this is the U1 contour in the physical domain, R and Z, in different time. When you do the rescaling variable, this is a self-similar variable, right? In this R variable, have to switch to the center of the maximum position, the position where you want to achieve the maximum in radial direction, and then the Z direction have to be scaled by capital Z, the location of the in the Z direction. So after you do rescaling, you see that the profiles that seem to converge to a self-similar profile. This is the U1 profile, and this is the vorticity omega 1 profile. In the physical domain, you can see the shrink and approach to 0. But after you do rescaling, it looks like you get a steady profile. And you can also look at the cross section for R cross section and Z cross section for U1 variable. In the physical domain, you can see that they approach into R0, the growing amplitude. But after you do the rescaling, it seems to collapse to a self-similar profile in both R and Z direction. So now, in the remaining few minutes, I would say do the same thing for the Navier-Stokes equation. So you will see the play out of almost the same set of pictures, because because the scaling seems to be compatible with the Navier-Stokes equation. So we wonder whether or not if you add a small amount of viscosity, it will still can survive the Euler singularity. And to my surprise, that if you add a very small viscosity, it will develop turbulent, the flow. It's not strong enough to regularize the shearing instability induced by the Euler equation. So it turns out at the end, I need to use a very large viscosity, 5 times 10 to the minus 3, which is very large. And you can see that the tornado singularity structure of the Euler equation is still preserved. In fact, the viscosity enhances water stretching, and I get a much larger amplification in the maximum vorticity. So this is the water line, the 3D water line. You observe a similar kind of pattern as the 2D Euler. So basically, the 2D Euler scenario is preserved, survived by the Navier-Stokes regularization. And moreover, because we use such a large viscosity regularization, you can see the vorticity, the dipole structure become original for Euler, get very, very sharp, like one-dimensional structure of the vorticity omega-1. Now you get a very relatively thick profile for the omega-1. Right? This is the dipole structure, which is the driving force pushing the singularity towards the origin. So originally, I plotted the radial velocity field and the axial velocity field. For Euler, you have a very sharp layer produced. But for the Navier-Stokes, you get the regularized, smooth version of the sharp layer. Again, you can see that the maximum, the U1 quantity is like the vorticity, one component of the vorticity vector. It's like a delta function singularity. Now, because of viscous term, you can actually get much closer to the potential singularity time. This is in the transform domain, you can get a very smooth profile in the rho and eta plane. So this is how the adaptive mesh work, right? So although the solution were really very close to the origin, at 10 to the minus 4 here, right? In the R direction and Z 10 to the minus 5. So from all the one region, all the way travel very close to the origin, this U1 and omega-1, right? You can see the mesh was designed in such a way they cover the most singular region. And then when the solution becomes smooth, you get to use a coarser mesh. So what is most surprising is that the maximum vorticity relative to the initial maximum vorticity, it has grown by a factor 10 to the power 7 by the time I stop my computation. I have never seen such a large growth rate for the maximum vorticity for 3D Navier-Stokes. This is honest 3D Navier-Stokes, no model, no approximation here, with a smooth initial data, right? That's so surprising. And if you want to try to check the Beer's law, the Beer-Catton-Maida number of criteria to see whether or not the maximum vorticity is integral in time, you can see the integral maximum vorticity also developed such a rapid growth, right? So it's pointed like you can see the nonlinear vortex alignment, U1 vortex preference of Z. For the Euler equation, you get a sharp gradient here, but now with Navier-Stokes, you get a regularized version. Because of the viscous regularization, the alignment becomes stronger in time for longer, right? So this is a vortex line alignment. We track how much at the position of U1, maximum U1, how large the value of preference of Z. We take the ratio. You can see it stay almost the same order for a very, very long time. And this is the early stage and the late stage. So this is the reason why we can get such a high amplification. For the Euler equation, I can only get to 5,000 amplification, which is already a lot for Euler equation. Yeah, but for Navier-Stokes, I can get 10 to the power 7. And that is most people would have claimed that they have already obtained a singularity for Navier-Stokes equation. So this is the trajectory where the maximum U1 achieved the R and Z position. You can see it start from order 1 region in very early time. In fact, the maximum is start from R0 and go out and then come back and to point out probably towards the symmetry, the origin. But unfortunately, the late time step, the ratio of the R and Z, it has maintained the order 1, the same single scale for a long time. But towards the end of the computation, develop a mild 2-scale structure. That somehow destroyed the singularity. So this is, we do a careful resolution study, the maximum vorticity indeed converge. You have the expected order of convergence. Again, you check the scaling for maximum vorticity and the maximum velocity field. You get the 1 over T capital T minus T broad with a logarithm correction. So it's certainly not integral in time. The velocity field, like 1 over square root capital T minus T, is basically set by the Navier-Stokes scaling. U1 omega-1 plot like 1 over capital T minus T, you get a very nice scaling, right? And the R and Z for a long time is scale like a square root T blow up. right? So again, you check the cell similar blow-up criteria for the profile, and like the oil equation, you can, this is the physical domain, this is the scale domain, you get something very, very similar, right? You get a cell similar profile developed, right? So this is the cross section. You can see look like a cell similar blow-up for the Navier-Stokes. And the pressure also go to negative infinity. That's one of the criteria for Navier-Stokes equation. If we blow up, the pressure has to blow up to negative infinity, right? You can see the maximum pressure inverse, blow up 1 over capital T minus T. And another quantity is the maximum vorticity L2 norm to the power 4. The L2 norm actually should be to the power 4. It's not integral in time. It looks like it also has a rapid growth, right? But however, if you do careful study, that actually is saturated. If you look at the zoom in the time against the log time, it seems to saturate. So that will give you a warning sign that Navier-Stokes may not blow up in finite time. But if you look at this, all these previous criteria, they all seem to indicate it blow up. And then finally, we're against the L3 norm of the maximum velocity field. It seems to have a large chance in growth, and then at the end, it dropped, it decreased. So this is a very strong evidence that Navier-Stokes actually avoid or escape the finite time law, right? Due to this very mild two-scale structure they're forming. In fact, if you check how the water stretching versus the diffusion term, and then you can see that actually diffusion term gradually taking over, become more and more dominant in time. So that may be explained why Navier-Stokes equation can barely escape the finite time singularity. So I run out of time now. So but at the end, we try to multiply the viscosity by a slowly decaying factor. The decaying factor is roughly like a log factor to minus power 4, which would depend on the solution, the maximum percentage of z multiplied z squared. So if the z squared indeed decay like a square root capital T minus T, we know that this guy blow like 1 over capital T minus T, it should stay order 1. Because the mild two-scale structure developed at the end, so this will have a very slow decay dynamically. Right? So we will compensate that. So we multiply the viscosity by a very slow decaying factor so that we can maintain the water stretching dominate diffusion term. And then we basically go through all the computation. I run out of time. I stop here. So you can see that then you have all the evidence that with a slowly decaying viscosity, the Navier-Stokes equation will blow in finite time. You can see the maximum vorticity amplified by 10 to the power 9. This is even larger than the Navier-Stokes equation. Right? So, and the double log of the maximum vorticity has clearly grown much faster than linear, right? So I'll stop here. So let me skip the last part. So let's jump to the conclusion. So I present some new numerical evidence that the 3D Euler equation develops potential singularity at the origin, which is very different from the scenario that I reported with Bordeaux, which has occurred at the boundary. And the Navier-Stokes equation with constant viscosity, relatively large constant viscosity, seems to develop finite time singularity, but then it somehow avoids the singularity due to the very mild two-scale structure developed in the late stage. But by modifying the viscosity with a very slowly decaying factor, roughly of this order, with a solution depending factor, it seems to then you can actually have a singularity develop. You can also consider this as like a vanishing viscosity limit of the Euler singularity, right, to some extent. But this also shows that the number of the Euler of the Navier-Stokes equation is kind of critical in a sense, because it just barely avoid blow up. But if you slightly break the barrier, the balance, then it can blow up. So I also presented some analytic attempt that using a computer-assisted proof, we have shown for the HL model, the 2D Boson equation with a weak initial class of velocity field, they develop finite time singularity. We're currently trying to push that maybe we can extend this analysis to C infinity initial data in the same setting that I did with Bordeaux. And this is some of the reference. Let me stop here. Thank you for your attention.
So thank you very much, Tom, for this exciting talk, which of course opens questions. So are there any questions for this, for Tom? So just let me begin with one question. You never mentioned if these solutions have a finite energy, but I guess they are.
But yeah, you have finite energy. That's a very essential criteria. In fact, this is periodic in Z, and so with a boundary in R, right, from 0 to 1. There's a wall in the R to 1. So that is this initial data is C infinity. So to certainly have finite energy. Yeah, we solve in the boundary domain.
Okay, and I had another, because you are speaking of tornado solutions. I was speaking that in nature, when you see very nearly singular phenomena like tornadoes,
yeah,
you have always temperature playing a role.
Exactly. The temperature here is like a U1 is like the temperature, because this is traveling wave singularity. So if you scale the solution, shift the solution and argue to move the center to this position, capital R, where the maximum U1 achieved, the U1 achieves the maximum value, then basically you can you can treat it like a approximation to the Busnet's equation to some extent if you have a two-scale structure. So the U1 plays the role of temperature density here. So that's why you have density variation. It's a sharp variation.
Mm-hmm.
Right. Okay. So for example, you can flow, if you're starting from here, it gets go up and then it's swirling down and then get outward, spinning outward.
Okay. Are there other questions? Yes.
There's someone raised hand, right? Luis.
Yes, Luis, maybe Luis Vega.
Yeah, hello. Thank you very much for your talk. I was wondering, you have been using this Bill-Kato-Maida criterion.
Yeah.
And I was wondering if maybe this other criterion by Konstantin Pfefferer-Maida could be better in this case, due that the direction of the vorticity seems to play a role, or really.
Oh, I see. That's very interesting suggestion. We have not checked that criteria for the Navier-Stokes equation. For it could be, but I think the main reason it is more due to the two-scale structure developed at the end.
Okay.
Yeah, because because then you have viscous diffusion dominate, right?
All right.
Only at the end. Right, because it's a logarithm correction. I mentioned it earlier. So you can see this. Yeah, this is the picture, right? So we try to track what is the competition between water stretching with the quadratic and linearity in the diffusion term. Because the Z go to zero like a square root capital T minus T, but divide by log some factor. So we towards the end develop a mild two-scale structure. The R and Z ratio become large. So that somehow making diffusion dominate eventually. That's why I need to decrease the viscosity coefficient to maintain the balance.
Okay,
I think that's the more key than the vorticity vector itself. Because the vorticity vector is very spinning like crazy, right, near the center of the tornado.
Bian-Wu, you had a question?
Yeah, let me ask a question. Tom, it's Ridgway Scott here.
Oh, hi.
Put on the very last slide with the references and leave it there for a little bit so I can start my reading.
Okay.
Very interesting talk, just fascinating to see
Thank
all
you.
of this, and an amazing collection of results. With too much to think about here, the variable viscosity is something I've been interested in. It's an interesting question how viscosity varies with the flow speed. This hasn't really been, well, there's some work that's been done at the molecular scale. A lot more needs to be done. There's an interesting question about tornadoes and whether, they mainly happen in Oklahoma. So there's something special about the air in Oklahoma. And by the way, in the summer, and I grew up in Texas, a little bit south of Oklahoma. I can tell you it gets very hot there, and all kinds of things may be different. It's interesting. So I just wanted to take a look at this and try to get up to.
I want to make thank you for your comment, but I want to say the later part of the work, it was inspired by this two-scale singularity that I studied with Do Huang using variable diffusion coefficient. But the one I presented here is constant viscosity coefficient.
Yes, I understand that. Yeah.
Right, because that one with two scale will not survive but the surprising thing is that even for this constant viscosity, in this case, because they had the Euler singularity has the same scaling as the Navier-Stokes, so it survived the Navier-Stokes regularization. So, but it still captured the tornado nature of this, the one that the two scale singularity I studied with Golo, with De Huang, with a variable diffusion coefficient. Some people challenging me ask that maybe the variable diffusion coefficient is not physical, right? So maybe it's an artifact because for that case where I cannot use a too strong diffusion, otherwise it will kill the Euler singularity. But here I don't have that problem. Yeah, in fact, a large viscosity help. That's kind of surprising.
Okay. Could you go back to the references just so I can?
Okay. Yeah.
It's my summer reading list here. I just want to know where should I start? Which the latest thing? The
latest thing it is the one that it's not the two scale singularity that reference not here. We posted on archive in February, but the one that I just reported here has not been written up. It's the first time I give a public talk to announce this result. It should be ready. I already almost written up all the results, but we should be out in a month. Yeah.
Very good, very good. Well, this is all recorded too, so we can go back and look at it.
Yeah.
Okay, so thank you very much, Ridgway. But Bian Wu had a question. Maybe you want to ask the question?
Yeah, thank you. Can you hear me?
Yes, yeah.
Okay, thank you for the great talk. I have a question about the geometry of the singularity case you just posed later.
Yeah.
Say, I also read your paper previously, like in 2014, about the singularity formation with the boundary.
Right.
It seems like the geometry of the singularity scenario in this case is much more complicated than the previous one, right?
Absolutely, yeah. That one that has a very simple structure. It is just a focusing, very stable. It's a stagnation point. This is a traveling wave. It's a tornado singularity. That one that does no spinning involved. Not spinning around the singularity, spinning around the axis, of course. Yeah.
Oh, okay. So it happens at one point in the axis, right? In the symmetry axis.
In the origin, right?
Okay.
That also it is also a stagnation point right here, right? So this is the dipole structure.
Okay. Well, when you say you are because you also have got some proof which is computer assisted proof for
right. That is for the case with boundary. Yeah.
Okay. So it's that is even with the most initial data is also for the case with the boundary, right?
Yeah, because that is the one that's most stable. With this one, the reason that the Navier-Stokes can manage to escape because there's some unstable mode. Right. Meaning that if there was a cell similar blow-up, the linearized equation have unstable mode, meaning that with the positive real part of the eigenvalue. So that's why it can can avoid. They have some unstable submanifold that it can escape.
Yeah.
But for the one with the boundary with the asymmetry, there's no unstable mode. Right. So that's why we just hope we can prove rigorously. We did prove rigorously for the C1 alpha.
Yeah. Sure.
Yeah.
Sure. Okay, thank you very much.
Thank you. Right, that is the slide summarized here.
Okay, so are there other questions? Or okay, so I think we will stop here. So thank you again, Tom, for this great talk. Very challenging results. For next week, we will have a talk by Roland Masson from Nice, and so I will stop here.